Have you ever wondered how engineers design those incredible bridges?
Oh yes.
Or how can we accurately navigate using GPS? The secret behind this amazing feast is trigonometry.
Hello everyone and welcome to my YouTube channel, The Untold Math Tutor, where we make math fun and approachable for everyone. I am JANICE'S and I am a first-year college student of Bachelor of Secondary Education, major in Mathematics at Pythagorean College of Agriculture, Sciences and Technology. Today, we're diving into the heart of trigonometry by deriving the Pythagorean identity and exploring the importance of trigonometry in real-world application. By the end of this video, you'll not only understand how to derive these identities, but also see how they apply to real-life situations. So, grab your calculators, get comfortable, and let's embark on the mathematical adventure together. I want to introduce you to the Pythagorean identities. First, we're going to look into why these things are so important in the study of trigonometry and how exactly they work, and then get into some examples of just using these identities. Pythagorean identities are these three guys here. And the first one here is probably the most important identities of Pythagorean identities. So the Pythagorean identities, we have sine squared theta plus cosine squared theta is equal to 1. And the second one is 1 plus tangent squared theta is equal to secant squared theta. And for our last identity is 1 plus cotangent squared theta is equal to cosecant squared theta. The first thing that you want to know about these identities is first, what on earth are they used for? Well, the most important thing about these identities is they help us simplify trigonometric expressions. A lot of times we get lost of different things in our trigonometric expressions. They can get very complicated, and these ones usually helps us crunch them down quite a little bit. Second, how on earth do they work? Well, you can take sine squared theta plus cosine squared theta is equal to 1 and build it straight from the Pythagorean theorem. In fact, that's why it has the same name, Pythagorean identities, Pythagorean theorem. They're really just trigonometric form of that Pythagorean theorem. But let's go ahead and take a look. In a Cartesian plane, let's plot a triangle. And as we all knew, that in trigonometric function, when we talk about sine of an angle, say theta, it's like saying take the length of the side opposite to the angle and divide it with the length of the hypotenuse. So just like here, sine theta is equal to opposite over hypotenuse. Similarly, when we talk about the cosine of an angle, it's like saying take the length of the side adjacent to the angle and divide it by the length of the hypotenuse. Just like here. Cosine theta is equal to the adjacent over hypotenuse. Let's assume that x here represents the adjacent of the triangle, and the y here represents the opposite side, while the r here represents the hypotenuse side. By that, we can say that sine theta is equal to y over r. While for the cosine theta, we can say that cosine theta is equal to x over r. Now, let's go back to our first Pythagorean identity, which is the sine squared theta plus cosine squared theta is equal to 1. And in our previous discussion, as what we have discussed earlier, the sine theta is equal to y over r. And for the cosine theta is equal to x over r. And we can easily substitute it here. So for the sine squared theta, we have y over r squared plus, for the cosine theta, we have x over r squared. It looks pretty good, but I could go ahead and square this in the top and the bottom. So it looks like this: y squared over r squared plus x squared over r squared. So as what you have noticed, they have the same denominator. So when having the same denominator, we can just put them together. So let's write it: y squared plus x squared is equal to r squared. So the question is, where did Pythagorean theorem comes into play? So remember, the Pythagorean theorem looks like this: a squared plus b squared is equal to c squared. The same thing with x squared plus y squared is equal to r squared. And as what you have observed in our numerator, it is y squared plus x squared, and it is the same with here. It looks the same here. So we can conclude that y squared plus x squared is equal to r squared. Now we can rewrite this as r squared over r squared, or they are the same or they look exactly the same, so I can say that it is equal to 1. So what does this really mean? It means that if I start with sine squared theta plus cosine squared theta, it does equal to 1. Now, if you understand the initial form of Pythagorean identities, you can easily figure out the remaining two other forms. Let me demonstrate how straightforward it is to do that. So, to derive the second formula or the second form of the Pythagorean identities, let's start with the sine squared theta plus cosine squared theta is equal to 1. And let's divide everything by cosine squared theta. And now we have sine squared theta over cosine squared theta. And remember that in quotient identities, sine theta over cosine theta is equal to tangent theta. Therefore, sine squared theta over cosine squared theta is equal to tangent squared theta. Plus cosine squared theta over cosine squared theta, it is obvious that it is equal to 1. Equal to 1 over cosine squared theta. In trigonometric identities, 1 over cosine squared theta is equal to secant squared theta. And now we come up with our second solution. And it is the same with 1 plus cosine squared theta is equal to secant squared theta. And for our third form of Pythagorean identities, let's do the same thing. Let's start with sine squared theta plus cosine squared theta equal to 1. But let's divide everything by sine squared theta. Let's divide everything with sine squared theta, divide this by sine squared theta, and divide this by sine squared theta. So we have here sine squared theta over sine squared theta, and it is obvious that it is equal to 1. Plus cosine squared theta plus sine squared theta. And remember that in quotient identities, that cosine theta over sine theta is equal to cotangent theta. Therefore, cosine squared theta over sine squared theta is equal to cotangent squared theta. And 1 over sine squared theta in trigonometric identities, 1 over sine theta is equal to cosecant theta. Therefore, 1 over sine squared theta is equal to cosecant squared theta. Therefore, we come up with our third form of Pythagorean identities. Alright, we are done deriving the Pythagorean identities. Now, let me show you examples of how nice this can be for really simplifying some expressions. So let's try to simplify this expression using Pythagorean identities. So, cotangent squared theta plus cosine squared theta plus sine squared theta. So, the first thing we need to do is to observe the expression. And, as what we have observed here, the 2 here is very familiar. Yes, it is very familiar, right? It is because it is found in the first form of Pythagorean identity, which is the sine squared theta plus cosine squared theta is equal to 1. Therefore, we can conclude that cosine squared theta plus sine squared theta is equal to 1. And copy the remaining plus cotangent squared theta. So now, it is more simpler than we had before. It's more simpler. This is more simpler than this. But actually, I can make it even simplified. So, as what you have observed here, cotangent squared theta plus 1, we can still simplify it with the third form of Pythagorean identities, which is cotangent squared theta plus 1 is equal to cosecant squared theta. Now, I only have one expression being squared instead of 1, 2, or 3 of them. So, amazing, right? Now, let's apply the Pythagorean identities in a real-life situation. A hiker stands at a peak of a 6-foot hill and asserts that the distance from their position to a tree at the base of the hill is 10 feet. The measurement of the hill to the tree is 8 feet. Validates the hiker's claim.
Now, let's identify the adjacent, opposite, and hypotenuse. So for our opposite, it is the height of the hill. So it is 6 feet. While for our adjacent side, it is the distance from the hill to the tree. So it is 8 feet. While the hypotenuse is the distance for the hiker's position to the tree, which is 10 feet. And the angle or the theta is between the adjacent side and the hypotenuse side, which is it is beside the tree. Before we will provide that the distance measurement is correct, let's identify first the value of sine and cosine. For sine, we have 6 over 10. Since sine is equal to opposite over hypotenuse, and opposite is equal to 6, and hypotenuse is equal to 10. Well, for the cosine theta, it is equal to 8 over 10. Since adjacent is equal to 8, and hypotenuse is equal to 10. Now, let's prove that the distance measurement is correct using the Pythagorean identity. We will use what we derived earlier, which is sine squared theta plus cosine squared theta is equal to 1. So it can be seen here. So sine squared theta plus cosine squared theta is equal to 1. So let's substitute its trigonometric composition, which is y over r squared plus x over r squared is equal to 1. Since we already know the value of sine theta and cosine theta, which is for sine theta we have 6 over 10, for the cosine theta we have 8 over 10, we can now easily substitute it here. So for sine squared theta we have 6 over 10, and let's square it, plus 8 over 10 squared is equal to 1. Now, let's solve the top part and the lower part. 6 times 6 is equal to 36. Or 6 squared is equal to 36. 10 squared or 10 times 10 is equal to 100. Plus 8 squared or 8 times 8 is equal to 64. And 10 squared or 10 times 10 is equal to 100. And since they have the same denominator, let us now directly add its numerator. So 36 plus 64 over 100. And 36 plus 64 is equal to 100. So 100 over 100. So now 100 over 100 is equal to 1. So we can conclude that the hiker's claim is correct using the Pythagorean identities, because the sine squared theta plus cosine squared theta value here is equal to 1. Amazing, right?
We are done deriving our Pythagorean identities. Now let's proceed to the importance of trigonometry in real world.
Trigonometry is not just a subject confined to textbooks. Trigonometry finds wide-ranging applications in solving real-world problems across diverse fields. Surveyors employ trigonometric principles for accurately measuring distances, angles, and elevations, essential for mapping land and defining property boundaries. In construction and architecture, trigonometry ensures structural stability and property alignment of elements, with calculation used for designing roofs, staircases, and beam angles. In physics and engineering, trigonometry aids in analyzing forces, motions, and energy, facilitating tasks such as determining projectile trajectories and analyzing mechanical vibrations. Navigation systems like GPS rely on trigonometric principles to determine the precise positions and distances on Earth's surface, enabling efficient navigation for various vehicles. Portions, while trigonometric functions are crucial in electronics for designing circuits and processing signals in multimedia application. These practical applications underscore the indispensable role of trigonometry in addressing the world challenges across different disciplines. To wrap up, today, we derived the Pythagorean identities and saw how they apply in real-world scenarios. The Pythagorean identity are just the tip of the iceberg in trigonometry, but they are incredibly powerful tools. I encourage you to explore this concept further and see how they can be applied to solve problems you encounter. Don't forget to like, comment, share, and subscribe for more math tutorials. Thank you for watching! Bye!